Hello everyone, we are Magnus, Andersson and Tuan representing the FlexiGrid project and Kankar, Bhattacharya representing the NESTNet project. FlexiGrid is funded by the EU while the NESTNet is funded by Natural Sciences and Engineering Research Council, NSERC, of Canada. Our presentation is entitled Enabling Flexibilities for Future Power Systems, Synergies from EU and Canadian Collaborative Activities. In this presentation, first we are going to present a brief overview of FlexiGrid with main objectives and planned demonstrations of FlexiGrid solutions to unlock the flexibilities in the distribution grids with high penetration of variable renewable generation. Then, we briefly present the identified collaboration activities between the two projects, FlexiGrid and NESTNet. Finally, we present also an overview of NESTNet and some selected example results from NESTNet based on which the collaboration activities will be carried out in the course of the projects. FlexiGrid stands for Enabling Flexibility for Future Distribution Grids with High Penetration of Variable Renewable Generation. FlexiGrid is still a young project which started from November 1st in 2019 with a total duration of 42 months. The overall aims of FlexiGrid is to demonstrate technologies and flexible markets enabled by IoT platforms for local energy exchanges and flexibility provision to DSOs for a secure, flexible and affordable operation of distribution grids with high shares of renewables. FlexiGrid is an impact-focused project where it was requested and driven by the needs of the distribution system operators for flexibilities. The project involves research and innovation actions to develop and provide innovative solutions for those needs. Starting from the project mission of unlocking flexibility resources and grid modernization, FlexiGrid will develop and demonstrate digital and innovative solutions at the grid edges, for example, IoT platform, peer-to-peer and peer-to-pool marketplaces, vehicles to grid, power to heat and power to gas, etc., as well as innovative business models, which will equip the DSOs with new tools to enhance the observability and controllability of distribution networks while supporting both pool-based and peer-to-peer market mechanisms for efficient real-time trading of energy and grid support services. These solutions will be demonstrated at real demonstrators to accelerate innovation development, thus increasing the societal impacts. FlexiGrid will build an integrated DSO-focused IoT architecture that brings together storage, demand response, variable generation, power-to-grid and power-to-heat technology. Deploy cutting-edge smart grid technology as an enabler. Further, it will develop and deploy innovative market models and enabling mechanisms that provide services to the DSO. It will develop and deploy innovative enabling commercial and contractual architecture. It will demonstrate FlexiGrid solutions by deploying into consumer premises, retailers, and DSOs across Europe. It will scale across Europe and globally by addressing barriers to innovation, developing financial instruments, identifying policy and regulatory issues, and collaborating across borders. This picture shows the main concept and architecture of FlexiGrid. The FlexiGrid integrated system consists of 4 connected layers. A customer layer, for example, a building energy management system and IoT platform clients. A grid layer, such as the DSO's SCADA. ICT layer, IoT platform and interfaces, and finally a market layer. Each layer exchanges information with the layers that is connected to the system connectors and the backbone infrastructure. IoT platform at the ICT layer will play a crucial role by linking the physical devices, network measurements, and climate data with the advanced calculation and optimization algorithms. This slide presents the expected outputs which will be developed within 10 main work packages, as shown, and 4 to 6 deliverables. The major outputs will include a scalable IoT platform for monitoring, control, and enabling energy transactions and grid service, tool for network observability and risk assessment and advanced real-time control of distribution grid, tools for flexibility determination, procurement, and dispatch, innovative designs of local energy markets with pool-based and peer-to-peer structures, sustainable business models and financial instruments, pathways for future market development, and DSOs. This slide shows the demonstrator at Chalmers University campus in Sweden. The picture on the left shows the campus, while the table on the right shows the major available controllable resources within a distribution grid of the campus. And these include, for example, PV panels, battery storages, EV chargers, a CHP plant, heat pumps, etc. At Chalmers demonstrators, we plan to demonstrate grid monitoring, control, and flexibility intervention in Work Package 5, with activities as shown in the table below, and local markets for exchange of energy and grid services in Work Package 6, with activities as shown in the table below. Flexibilities using P2P or blockchain mechanisms will be demonstrated at several demonstrators in Bulgaria, Turkey, Switzerland, and Belgium, as shown in the picture. Flexibilities from local energy storage and EVs will be demonstrated at several demonstrators in Switzerland and Turkey, as shown in the picture. FlexiGrid solutions will be developed by the consortium consisting of 15 partners, as shown in the picture, and from 7 countries. FlexiGrid has planned collaborations with the NESTNet project in Canada. The collaboration activities and the NESTNet project will be presented next. The picture shows the areas for collaborative activities of the 2 projects, which are the overlapping area of the 2 circles above. The scope of NESTNet is closely related to the scope of FlexiGrid in terms of developing technology, market solutions, and policy recommendation for enabling energy storage integration into the power systems to enhance the hosting capacity of variable and renewable generation. The collaboration activities are found mostly in Work Package 3, 5 to 7 of FlexiGrid, and the Theme 3 and 4 projects in NESTNet. This collaboration aims to increase the understanding of different technological needs and developments, and different market environments, as well as policy and regulations in Europe and Canada or North America. Maximize the impacts and values to stakeholders from both projects through the synergies that could be achieved from each project by facilitating exchanges of researchers, for example, short visits of PhD students and senior researchers, joint research and demonstration activities in common areas to maximize the use of resources, both personnel as well as infrastructure. Sharing of expertise, knowledges, measurements data, models, etc., to the extent possible as agreed by both consortiums. Supporting development activities by commercial partners within both projects to bring their innovations closer to the market. And finally, organizing joint meetings, web as well as face-to-face from both consortiums. In the next section, we will present the NESTNet project. In this section, we will present an overview of NESTNet project and the projects which are collaborating with FlexiGrid. NSERC Energy Storage Technology Network explores different types of energy storage while determining how best to integrate them into electricity grids. It considers the implications arising from increasing adoption of energy storage and consumers' adoption with these technologies. Towards a strong domestic Canadian energy storage industry that is also competitive in the global marketplace. The NESTNet principal investigator is Dr. Bala Venkatesh, who is a professor at ECE department at the Ryerson University in Toronto, Canada. NESTNet by the numbers. When it comes to funding, there is $5.2 million from NSERC. There is $3.5 million from partners. researchers, there are 15 Canadian universities involved and 27 faculty members. There are 26 researchers from the industry and government partners. The research themes are 4, and there are 24 research projects, and there are 350 HQPs, such as master's degree, PhD, and PDF. The NESTNet outcomes in terms of numbers until end of year 5 are 9 patents, 536 journal articles, conference papers, and other outputs, 124 graduates, of which 80% will be employed in the energy sector. There plan to be 93 events held with 1,987 event participants. The NESTNet research themes. Theme 1 is energy storage technologies, which consists of 6 projects. Theme 2 is power electronic converters, which consists of 5 projects. Theme 3 is power systems integration, consisting of 7 projects. And there's a project 3.5 is operation and control of power systems with energy storage, which we will develop further in this presentation. Theme 4 is entitled Economics and Policy, and under this is one project 4.3 titled Provision of Ancillary Services by Energy Storage Systems, which we also will develop further in this presentation. Project 3.5, Operation and Control of Power Systems with Energy Storage. The lead here is Professor Claudio Canizares. The collaborator is Professor Kankar Bhattacharya. This work involves developing mathematical models of ES systems accounting for operational features and constraints and integrate with power system operations tools. At the distribution system level, optimal operation will examine and derive benefits from ES systems to manage increased renewable integration, feeder loading management, arbitrage, etc. At the transmission level, optimal operation will examine the use of ES for frequency regulation, energy arbitrage, etc. Project 4.3, the provision of ancillary services by ESS. The lead here is Professor Kankar Bhattacharya. The faculty collaborators are Professor Claudio Canizares and Professor Mehrdad Kasirani. The industry collaborators are Dr. Stephen Wang, Dr. Mohammed Ahmed. This involves examine the role of ES solutions as ancillary service providers and their integration with the grid system. Determine the cost structures and appropriate pricing mechanisms for these services. We're going to present example results from Project 4.3, Market Participation and Planning Frameworks for Energy Storage Systems, and the researcher here is Hisham Alharbi. So some example results from this project are: 1. Proposed a new framework and stochastic mathematical model to determine the optimal BESS plan for a microgrid, considering different technologies, including energy capacity, degradation, and uncertainties of renewables. 2. Developed a multi-objective model to determine optimal ESS investments, considering their degradation by a third-party microgrid. 3. A bi-level approach is developed to determine the strategic participation of pumped hydro energy storage, PHES, in electricity market. Example results from Project 4.3, Flexibility Provisions from Energy Storage Systems and Loads in Smart Grid. Researcher here is Omar Al-Rumai. One example is developed a novel concept of residential energy hub, so-called REH, flexibility index to quantify flexibility resource available from an REH. 2. Developed a two-stage coordination scheme that takes into account distinctly individual objectives of each REH as well as that of the LDC. 3. Created new revenue streams for RHSs to render BESS and DMS financially attractive for customers in LDC. 4. The proposed model accounts for unique set of preferences, behavior, and bus locations, customers with different objectives, and different types of ESS. Thank you very much for your attention. We are open for any questions or comments.